Hi, doctor.
Sorry.
Oh, no problem. This is an objective one optimized head disposition design, and I place hyacinth of different materials in water and test which material can produce better head disposition effect under the same environmental conditions. I used three materials: aluminum, copper, copper ore, and I got this result is that we can see the hyacinth using copper material has the best head dissipation effect. This is the graph. This chart shows the temperature changes at the top of hyacinth. The top surface of hyacinth is the surface in contact with TEG. This is copper.
Which part?
The blue line is the average temperature of hyacinth. Is the blue line.
Sorry, can you go back up?
Okay. The surface. This is TG, and this is the surface of hyacinth.
So this TEG, you have ceramic material on the top. What kind of material on the top?
Sorry.
This TEG.
Yes.
The top one. This one. What kind of material?
Aluminum oil is TG.
Alumina.
Oil. Aluminum oil.
Aluminium oxide.
Oil.
That is the heat sink, right? Copper alloy.
TG is aluminum oil.
This one alloy.
Yeah, TG is oil.
That is alloy? Are you sure?
Aluminum. And
this is heat sink, right? Copper alloy heat sink.
Yeah. TG is aluminum and copper oil. TET. Yes, this material is aluminum, and but it is not TEG. Sorry. This is TG. This is copper oil, and this is aluminum. This is aluminum.
Sorry, this one what? Copper alloy?
Yeah, this is TEG.
What is the material?
Copper alloy.
Copper alloy.
Yeah.
Both.
Both.
This one?
Uh,
This one.
this one, all of them is copper alloy.
Why?
Sorry.
Why you use all copper alloy?
粗略的设计去看传热。Roof design to look at heat transfer because I think the heat to see the heat is important in this part. So I gave the TEG is
the TEG.
yes.
Currently, what is the role of that TEG? What is the function of that TEG? For cooling or what?
I don't consider it.
So why you put TEG over there? Can you go to your slide?
Okay.
Sorry. Okay, so right now you said that this is TEG
Yes.
and there is heat sink, right?
Yeah,
Inside the water.
Yeah.
What is the role for that TEG? Why you put TEG over there?
Just put it.
Hmm?
Just put it.
Just put it
Yeah.
for no reason.
No reason.
Can you go to your title?
Oh.
Okay, so right now you are doing to this floating solar cell, right?
Yeah.
And then you put thermoelectric module. Why? If you don't want to use the thermoelectric module for anything, why you put it, right? Just take it out, right?
Yeah.
So right now you just want to reduce the temperature of solar cell, right?
Yes.
Then why you put your TEC if you don't use it?
I don't use TEC. I use TEG. Yeah.
Why you put TEG if you're not using it?
Because they have the temperature difference. And the TG can improve the efficiency of all of the system I want to design.
How it will improve?
Like this. I think we can come back to last week. Oh no.
So you are using the TEG for what? For produce what?
For to get more
Power.
power to help the solar panel to help the system improve the system's
Okay.
efficiency.
So you want to harvest the energy to produce electricity by using the TEG. Am I correct?
Yeah, yeah.
Okay. So right now, currently, you use all the thermoelectric element inside the TEG is the copper alloy, right? You are using all copper alloy.
Yeah, I use copper alloy.
It's not TEG.
It is easy, but I want to simulations to get the temperature difference, so I didn't give some more flexible material of the TZ, just copper alloy.
You cannot do that. Material have different properties.
Yeah, I know.
If you use copper alloy, the result will be different.
Okay. Yeah.
You need to use the real TEG over there.
Okay.
If you put copper alloy and then the outer material is aluminium, it is not at all as a TEG. Because all are metal.
Yeah. Okay.
All are electrically connected.
Yeah.
That's why I'm confused. You want to use TEG for what? If you only want to make a heat dissipation from this photovoltaic cell, no need to put the TEG, right?
Okay. Okay. If the TZ is right, we can get this reason.
This result is totally not correct.
Yeah.
We cannot discuss it.
Okay. And after that, I changed the I changed the contact area between heatsink and water to see which one can achieve better heat dissipation effect, and I can get this. Type C is the best. Yeah.
The method is okay. But right now your simulation is wrong.
Okay.
You need to correct your TEG.
Yeah.
Okay.
Yeah.
So you have two parameters. One is the material of heatsink. You change 3 material of heatsink.
Yeah.
And then you change the depth inside the water, right?
Yeah.
Other than that, two parameters only.
Two. Yeah. B and C.
One of the parameter you change the material of heatsink. Aluminium, copper alloy, right?
Yeah.
And then the second comparison, you change the depth.
Yeah. After that, I found copper is the best, so I use copper to do it. Yeah. And I changed the contact area. It has the biggest contact area between heatsink and water.
How you make it different contact area?
I add this thing. It has 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Is 10. Is 11.
Okay. The numbers of fin.
Yeah. Numbers of. Yeah.
Why you choose that numbers of fin?
I just want to get a bigger contact area.
Why you right now 9, 10, 11, right?
Yeah.
Why not you do 1, 5, 10?
Oh.
You need to have justification when you want to change the parameters.
Okay.
Okay, so right now you did two comparison. One is the material.
Yeah.
The second one is the numbers of fin.
Okay.
Only this one? Only these two right now?
Yeah.
Right now what you have did only these two?
Yeah.
Only these two. Can you add one more?
I don't know.
How about you make it one more, the thickness?
I didn't consider it.
So can you add it? Can you consider that?
Okay.
At least you need to have 3 kind of parameters.
Okay.
Okay?
Okay.
And then when you choose how big the thickness, you need to have justification. How much the numbers of fin, you also need justification.
Okay. This is my objective 1. And this is what I am doing in this week is my objective 2. The application feasibility of PCM partition design. I divided this objective into 2 parts. This is part 1. Because the PCM operates differently during the day and night, I first consider the application of PCM during the daytime. Okay, is the step 1. Simulate PV panel to measure the temperature transfer under the specific light intensity and then calculate the output power and efficiency. But I didn't finish the step 1, and then I want to simulate PV and paraffin. Paraffin is the PCM to observe the temperature of PV panel under the semi-environmental conditions, and then calculate the efficiency and the output power. And then the step 3 is PV and PCM and copper. Like this, observe the temperature of the PV panel under the same environmental conditions, and then calculate the efficiency and output power. This is my part 1 of the objective 2. And then is part 2. If it's determined that the design of PV and PCM and copper can provide better efficiency, then we need to consider the situation at night. This is my design idea. Simulate PCM and copper through ANSYS to obtain the temperature change curve within a day. Obtain the working state of PCM and copper at night, and then calculate the working condition of TZ under this condition to see if it can support TZ to continue work at night. Yeah, this is all of my objective too.
The approach is good. Okay, the approach is good. But you need to make the sentence this sentence.
Yeah.
You need to just rewrite the sentence. Can you go back to the previous slide, the second one? Okay. No. Okay, the second one. So right now, you have 2 kind of structure over here, right? You make a comparison, PV paraffin, and then the second one bilayer paraffin and copper.
Yeah.
Okay. And then I can see over there, you want to also change the shape, right? It's not all paraffin, but some part paraffin, some part copper.
Yeah.
Okay. So that can be your step 4.
Step 4?
Can be your step 4 over here. Because you need to find the optimized size of that paraffin and copper. Because how can you know this kind of shape is the optimized design? You cannot know, right? So you need to change the size.
Okay. Okay.
So add one more over here.
Okay. this is my objective story. Is to explore the efficiency improvement of overall design. This is my design idea. Integrate data, calculate the overall design efficiency of PV and TG and
Is
PC.
it you have enough time?
I don't know.
I think you don't have enough time.
Yeah.
So no need to do this objective 3. Can you go up previous? One more. But second, make this one just I said about the shape.
Oh.
Make it as a objective 3.
Okay. Okay. And this is my plan.
But how can you go back? Go up. When will you attach the TEG and this solar panel? No, you not attach.
No. Yeah. No.
Right.
Yeah.
I suggest you, because you don't have enough time with it. So change your title right now to improve the heat dissipation of floating solar panel. So you just focus on heat dissipation. Okay. So for your first objective, you are improving or you are investigating the influence of heat sink material film thickness and the numbers of fit. Okay. Number two is to improve the heat storage, right? This one on the this one. If you want to make the heat storage, you still need TEG, right? It's not for the floating solar panel. So this one are not for floating solar panel, but for the floating thermal electric power generator. Okay. Because if you want to store the heat, it's not for the solar panel.
Just for it.
So improve the heat storage for to investigate or to propose storage for PEG, for floating PEG. Force and heat storage for floating PEG. Number 3, to investigate this one is to investigate the inflow of PCM, single PCM layer, and metal PCM B layer for heat storage. Okay. And number 3, to propose and optimize design of metal PCM B.
Okay.
So this one you need to simulate the heat sink pipe. The heat sink pipe. This heat sink pipe, you need to change at least 3 kind of material.
Yeah.
And then at least 3 kind of thickness, and then at least 3 kind of numbers, fin numbers.
Okay.
And then make it systematic. For example, if fin numbers, maybe you can start 1, 10 or 100 maximum that can insert over there, depending on the size.
Okay.
Thickness, also make it systematic. 1 millimeter, 1 centimeter, 1 meter.
Okay.
Like that.
Okay.
Maybe. Okay. And then 3 kind of material you need to choose depending on material properties like the thermal conductivity and also the heat capacity. Okay. So you need to choose a different kind of material depending on that thermal conductivity and heat capacity. Okay.
Okay.
This one, the parameters, there are 2 kind of layer. Okay. One is only PCM. Okay. But this one, you need to put the contact with alumina, right? Because this is the top part of the TEG metal, right? So this PCM, at least you need to have, because you have 2 kind of structure. Okay. PCM, please find 2 kind of PCM material.
Okay.
Okay. So this is for single. Much better if you can have 3 lah.
Okay. Okay.
And then for the B layer, so you have alumina, and then you have the PCM. the metal you want to make it in contact with the TEG or on the other side. That one you need to check. Yeah? Why you want to put the metal? Right? Why you want to put here or here? Not sure. What is your thinking? Yeah? You need to justify why you want to make that one layer is the metal layer.
I'm not sure.
Hmm?
I don't know.
Because you just tell me that you want to put copper and paraffin, right?
Yeah.
Why?
Oh.
If you want to make this kind of B layer, you need to have justification.
I want to get a better temperature difference.
So maybe it's in here, in contact with alumina. I don't know. You need to simulate. Okay. So this one also metal. At least you have 3 kind of material.
Okay.
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 So this part, PCM, and then these are alumina, TEG, and inside the TEG you have the lead, right? You have lead. And then again alumina, right? And then this one, the heat sink.
Yeah.
Okay.
Yes.
So this heat sink, when you simulate, it's better to put also alumina on the top. Yeah?
Okay.
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 And then the heat source, you use irradiation, right, in your simulation, or you fix at one temperature.
Sorry?
When you simulate the heat sink,
Yeah.
this hot side, how you give the heat to the hot side?
The sunlight.
So this also the sun irradiation, the heat source. This one, I think no need to have the sunlight because the sunlight is on the top. This one at fixed temperature. For example, from here, when you do this simulation, you find out this temperature is 40 degrees. So you can use this temperature and then you vary it. Maybe from 40s or 30s degree, 300 Kelvin until around 450 Kelvin, for example. Okay. This number 3. Number 3 is the design. So this one you need to change the shape, right? For this one. So you have one shape which is the whole. So this is aluminum. Maybe this is the metal and this is the PCM. Or metal in the fine, I don't know. Depending on this. So this is one shape. The second shape, maybe change. This is metal. This is PCM.
Oh.
The second shape. The third shape, you change the size. Okay. Maybe first you change it half, for example. So this is aluminum. For example, you have half of it is PCM, half of it, and then you reduce it more. For example, you change it into what shape? You divide by 4. 4 and then more smaller. We have maybe.
Okay.
Systematic. You need to be systematic.
Okay.
Okay. I think this one you have enough time lah. Based on your progress right now.
It is better. Thank you, doctor.
Just consider back the sentence. This one I also don't write down the full sentence. Okay.
Okay. Thank you.
Please don't forget.
Thank you so much.
You must be fast. Right now it's before.
Yeah.
I hope next week I can see the result for first objective.
Okay. Thank you, doctor. Thank you.
Anything else? Anything else? Dah habis lah.
So like based on last week